So let us see how a differential phase shift transmitter and receiver works. So this is a non-coherent type of modulation wherein we have the logics or the digital data being transmitted over the channel with the help of continuous waves. So let us consider how this modulation works. So firstly we have input binary sequence or any data bits that has been coming from or being received from a digital source. That might be a train of zeros and ones that is fed to a logical network. A logical network might be anything, any logical circuits which performs an operation on my digital data, or which I am going to translate from one form to another form. So this is how a logical network works. Logical networks is nothing but any digital circuits. So any digital circuits like your gates, basic gates, anything that performs an operation on input signal, a function basically. So you will be getting d of k, or a differentially encoded signal. I can call this as a differentially encoded signal. So basically I have a feedback which is delayed by a bit period, 1 bit period TB, and that is being fed back to this logical network, so that whatever the binary data I am getting, that data will be differentially encoded with respect to this delayed version of its own. So then that will be shifted, or that will be passed on to amplitude level shifter, wherein this amplitude level shifter just shifts the amplitude, and from there I'll be having a product modulator wherein, depending on my data bit stream or the differentially encoded bit stream, I'll be getting a signal being modulated out of the DPSK. So if there is a bit 1 being transmitted, then the signal root of 2 by TB, 2 over TB cos 2 pi f ct will be transmitted, and if there is a bit 0 to be transmitted, then a phase shifted version of the same signal. The signal will be same, that is root 2 over TB cos 2 pi f ct, with a phase shift of pi, or the phase shift will be advanced to pi degree radians or pi radians, and that will be transmitted, pi radians will be transmitted. So this is about the DPSK transmitter part. This part is about the DPSK transmitter part. Now let us check with the receiver part, wherein receiver part is nothing but you will be receiving the x of t. X of t is nothing but your DPSK signal, that is a continuous waveform that we have transmitted, and that signal will be received at the receiver end. Will be passing it through a band pass filter to confine it to a particular band which we already have been transmitted, because we know that channel will be inducing some noise, so we'll be filtering it out, and that signal will be multiplied with its own delayed version, and that multiplied version will be taken up with an integrator. So this whole block, this multiplier and the integrator part together performs an operation called correlation, or it is basically finding the match between current and the previous, and we are integrating it. So this is what correlator does, and correlator gives output value L. If this value L is lesser than 0, then the output bit stream will be 0, and if it is greater than 0, then this addition device takes addition, that the output bit is 1. So by this I'll be getting data at the output, ones and zeros. So what are the data I have inputted over here, so that data will be received at the output. So this is how DPSK transmitter works. And let us see a problem. So given a binary sequence 1 0 0 1 0 0 1 1, so if it is applied to my DPSK transmitter, then they may ask you to sketch the waveform. How to sketch the waveform? So basically a DPSK transmitter is very simple. So this is what the logical circuit just we have discussed. So this is a logical network which has been shown here. So the logical network here is just an XNOR gate. It is XNOR gate. Okay. So I'm having a input message signal, a binary data sequence that has been given as 1010011, and that is been XNOR'd with a delayed version of DK. So I'm going to take two conditions, condition 1 and condition 2. So you can take anything, but just mention which bit you are going to consider to be as initial. So initially if I take 0, that is the initial bit of the output or the decay, the delayed version of decay 0. So 0 will be XNOR with my value 1, input value 1, and 0 XNOR 1 is 0. And this is how you will be taking this output value with the delayed version and you will be XORing with the input. So by doing this, 0 XNOR 0 is 1, 1 XNOR 0 is 0, 0 XNOR 1 is 0. So like this if you do, you will be getting the differentially encoded vector or data. So this is one part, and this is another part. If I am assuming the initial bit to be as 1, so what happens? So 1 XNOR 1 is 1, then this 1 XNOR 0 is 0, 0 XNOR 0 is 1, 1 XNOR 1 is 1. So likewise XNORing operation you do and you will be getting a differentially encoded stream. So this is the differentially encoded stream. And what we are basically going to do is I'm going to represent a phase. I already mentioned that. So I'll be having a product modulator wherein it will be taking out the data stream, and depending on this data stream it will be modulating my signal or my data, digital data, with an analog signal or a continuous waveform, I can say. So for a bit stream 1 there is no phase shift, or it is just the same signal being transmitted through 2 by over TB cos of 2 pi Ct. And for a data stream of 0, I'll be having an advance, or the signal will be advanced by a degree radians of pi radians, it will be advanced. So this is how sinusoidal signal look like: 0, pi by 2, pi, 3 pi by 2 and 2 pi radians. This is how the degree which we all know. So basically what I'm going to do is wherever I have bit 1 there is an actual signal being transmitted, and wherever I have bit 0 I have the same signal which is advanced by a pi radians, so that will be transmitted. So this is how the data for this, the differentially encoded data, I will be getting this. So for that data I have represented the phase shifts. So for every bit period, so this is a bit period TB, so this corresponds to 1 bit period TB. Okay, likewise 1 TB, 2 TB, 3 TB and so on. So what I have done is for every TB I have taken 3 cycles. So this is 1 cycle, this is 2nd cycle, and this is 3rd cycle. Okay, so for every period I have taken 3 cycles. So for bit 1 I am going to consider just a sinusoidal waveform. Okay, this is one sinusoidal waveform. And for bit 1, so from 1 to bit 0 I have a phase shift of pi, or I have an advance of pi radians. So this signal, actual signal, is now been advanced for pi. So that is, if this is my original signal, this signal will be advanced by pi radians and this will be transmitted. So again 1 cycle, 2 cycle, 3 cycle. So for every bit period I am taking 3 cycles and I am representing each of my binary data, that is differentially encoded data. So if you keep on doing from 0 to 1, again there is a phase shift of pi again, because pi is your actual signal which was previously been transmitted for the 2nd time period. Then the 3rd time period you have bit 1, whereas there is 0 degree, that is this signal should be transmitted. So I am going to take that signal and I am going to transmit. So after this, the next bit period again I have 1, so there is no phase shift, the same signal continues, and wherever there is phase shift I have this phase change. Hope so this will do good. So this problem might be there, so better go through it. So please let me know if you people have any doubts, if I can help you out in understanding this problem again, I can do it. So cheers.